When an HPLC system loses pressure or shows unstable flow, the root cause is very often a pump leak. But not all leaks are visible, and many are internal. One of the most reliable ways to diagnose these issues is a technique called pressure isolation. It allows you to pinpoint exactly where pressure is being lost, without replacing parts blindly. The principle behind pressure isolation is straightforward. Liquids are only slightly compressible, and the hydraulic volume inside an HPLC system is tightly confined. If you pressurize the system and then stop the flow, the pressure should remain essentially constant. If it decays, that pressure loss must be caused by either a leak or trapped gas. By isolating different sections of the system and repeating the test, you can localize the problem with high confidence. Pump leaks matter because even very small losses, on the order of a few microliters per minute, can cause measurable analytical problems. These include retention time drift, poor gradient reproducibility, unstable baselines, distorted peak shapes, and reduced sensitivity, especially in LC-MS systems. Upstream leaks are particularly problematic because they alter solvent composition before mixing, creating gradient bias that often gets misdiagnosed as a column or detector issue. The diagnostic process starts by removing the analytical column and installing a back pressure restrictor. This allows the pump to generate pressure safely without risking column damage. Under normal operation, the pressure should be stable with minimal ripple. Any visible solvent at fittings or the purge valve immediately indicates an external leak. Next, you perform a static pressure hold test. The system is pressurized, typically around 100 to 150 bar. Then the flow is stopped, and pressure is monitored for several minutes. As a practical guideline, a decay of about 1 bar per minute or less is generally acceptable. Faster decay suggests a leak or trapped air. If pressure loss is observed, isolation begins. By capping the pump outlet directly and repeating the test, you can determine whether the leak is downstream, such as in the mixer, pulse damper, or tubing, or internal to the pump head itself. Internal leaks most commonly originate from worn piston seals, fouled inlet or outlet check valves, or a purge valve that does not fully seal. Pressure decay can even be quantified. Using the known compressibility of the solvent and the system's internal volume, pressure loss can be converted into an approximate leak rate. Even a few microliters per minute, while invisible, is analytically significant. After any repair, both static and dynamic tests should be repeated, followed by system suitability checks to confirm stable pressure, accurate gradients, and consistent chromatographic performance. In summary, pressure isolation is a physics-based, systematic method that removes guesswork from HPLC pump troubleshooting. It allows analysts to distinguish pump failures from downstream issues quickly, objectively, and reproducibly, saving time, solvents, and unnecessary component replacement.